The speaker expresses thanks to Hubei Zhonghe Institute of Geology and Environmental Technology for the invitation as keynote speaker. Today I will be speaking on the topic numerical investigation on combined influence of cavity and liftad profiles on combustion characteristics in scramjet combustor. And in fact, this work has been done by one of research scholar of the department and where one more guide is also involved. Then the outline of my presentation are introduction, this comprises of application and motivation, state of art, literature review, then research guide, then objectives, then problem definition. Then we have discussed theoretical formulation, numerical procedure, then validation, then results and discussion, conclusion, and finally references. Okay, then I would like to express first of all, there exists one turbo engine which it can operate up to Mach number 3 and where moving parts are there and flow at the inlet is subsonic. And in ramjet engine, moving parts are not present and flow at the inlet is supersonic. And in scramjet engine, moving parts are not present and flow at the inlet is supersonic. Then we can say that turbojet engines are efficient and able to produce high specific impulse. Means for turbojet engines, the specific impulse, it is very high. And for ramjet engines, they are useful for Mach number up to around 5 or 6. Means after 5 or 6, the efficiency decreases. And then scramjet can provide good specific impulse up to high Mach numbers, and hydrogen fuels, they are more attractive for the hypersonic flight regime than hydrocarbon fuels. Then the performance of rockets is constant over the whole Mach number. And this is the diagram which describes everything, that is variation of specific impulse at various jet engine. Then the scramjet supersonic combustion ramjet, this is improvement over ramjet. The airflow in the combustion chamber should be maintained at the supersonic speed. Combustion is achieved through the continuous injection of fuel in the supersonic condition. The fuel mixes and combustion increases the pressure and temperature, and the flow expands through nozzle to produce thrust. And here in the diagram, we can say that there is inlet section, then isolator is there, then combustion one inside one strut is also we can see. And what is strut? This we will come on this at later part of the story. And here the convergent inlet is there and compression and deceleration of incoming air is there. Then isolator. So the function of isolator, the isolator acts as a bridge between the combustor section and inlet section. And combustor, gaseous fuel is burned with atmospheric oxygen to produce heat. And divergent nozzle, heated air is accelerated to produce thrust. And this is shown from the diagram also. Then this is about advantages and limitation. And limitation is lack of stealth is there and need of boosting to high speed around Mach number. Then this requires scramjet engine, this requires an additional propulsion system. Then there are civil applications, means maximum scramjet speed can be as high as 15 times the speed of sound. Then drastically this reduces the travel time. Like we can go Tokyo from New York City in a 2-hour flight. Then high-speed transportation we can hope by 2050 or before that also. Then there are military applications in surface-to-air missile, then air-to-air missile, then Russian Indian BrahMos supersonic cruise missiles. So these are military applications. And after that, the scramjet, it is well suited for hypersonic propulsion in the range Mach number 5 to Mach number 25. Then first theoretical studies and patents of ramjet principle obtained in 1920s. Then 1938, the first engine, that ramjet engine was developed. Then next, that atmospheric depth it is done. So mostly we see that the work in experimental work in this direction. This is done in Australia, USA, and Russia, and France, Japan, and India. They are also having hypersonic program. Then 2016, ISRO launched Scramjet 2 is a solid fuel rocket. Then this aircraft forms an important component of the country's hypersonic cruise missile system. So, combustion in one application differs from combustion in another area by the relative importance of the various phenomena based on fuel, then geometry, then operational conditions. So, this is all introduction about the combustion phenomena. And here in scramjet engines, we observe rapid mixing, then short combustion time, very short, then proper flame stabilization is there. So, and after that, the there are cavity flame holders, which, and it is shown in the figure. Then it is implemented for the first time in a joint Russian-French hydrogen fuel dual mode scramjet flight test. It is given in reference 78. Then 1994, NASA collaborated with CIAM for the investigation on dual mode scramjet with a cavity flame holder. The location of a cavity flame holder is a crucial factor in a supersonic combustor. So cavity here we can see in the diagram that the primary vortex is there, then one secondary vortex is also there, and the recirculation zone, it is inside the primary vortex. Then there is transverse mechanism also, and then longitudinal mechanism also. So these are the flow features of cavity. Then in open cavity, shear layer separates from the upstream lip and reattaches to the back face when the L by D ratio it is in between 7 to 10. Then we called closed cavity flow, where the separated shear layer reattaches to the bottom wall of a cavity for L by D ratio in between 10 to 13. So here we can see about the cavity that these are, we can observe the streamlines obtained from a Reynolds average Navier-Stokes range computation, and cavity length and closeout angle affects mean recirculation zone flow field. Then second is streamline patterns show expansion of primary vortex relative to secondary vortex over the one baseline case. Second as either the closeout angle is decreased below 90 degree or the cavity to length to depth ratio is increased in that case. So here we can see different type of strut. That is triangular strut, we can see in the figure, then wedge-shaped strut, and then alternating wedge strut. This is also there. Then the strut base acts as a flame holder by creating wake behind it. And the strut injectors play a major role on the formation of oblique shocks. and the strut injector is arranged in the central location of the combustor to inject the fuel flow parallel to the free stream air. And then we can see here the structure of the strut, and we can see the shock wave also, and stream-wise vorticity that is initiated at the back of the strut, and two expansion fans there at the middle of the strut. So mostly for scramjet, hydrogen is the most promising fuel that I would like to say, and due to rapid atomization, vaporization, then faster dissipation rate, then eco-friendly nature, then lower molecular weight, then higher flame stability, which produces efficient mixing and combustion in supersonic flows. Hydrogen leads the race owing to its better features. So here we can see that the flame is stable due to the propagation of shock waves, then cavity flow oscillation, then due to cavity recirculation zone and complex combustion process. In fact, the scramjet combustion, this is complex combustion process, and this requires flame stabilization and difficulty in prediction. And here we have taken turbulent diffusion, then finite rate chemistry model we have chosen. Then combustion becomes unstable due to poor combustion. And shock train reduces the ignition problems otherwise. External igniters such as plasma torch and saline injection are necessary for good ignition. Then there is parallel injection, then normal injection, then transverse fuel injection. These are three types of injection that are used. Then the flame stabilization techniques, I will say that cavity, then strut injector and diverging combustor wall. These are three flame stabilization techniques. And in fact, there is lot of literature review discussed on this, and huge amount of literature is available on this area, and mostly experimental work is done in USA, China, Australia, and Germany. So these slides in speed of discussing, as I am not having much time, so I would like to keep these slides. So this is the diagram of dual cavity. Then this is strut injector. Then we are having triangular and diamond and wedge type of it also injector. So, now I will come on research gap. That lack of study, considering the combined influence of cavity strut-weft scramjet combustor with various cavity parameters, namely L by D ratio of cavity and angle of cavity, it is not discussed. Then numerical investigation on influence of dual cavity with strut location on combustion characteristic has not been reported. Then third one, the reacting and non-reacting flow conditions found in the existing literature have used hydrogen fuel, but the comparative analysis of hydrogen and ethylene fuel for a range of Mach numbers was ignored. And fourth, very few studies have been carried out on the effect of various strut profile in the scramjet combustor with a cavity and it needs further applications. So this is our objective one, that is comparative assessment of a combustor with a cavity and a combustor without cavity, and effect of L by D ratio of a cavity and effect of angle of a cavity. This we have discussed in objective number one. Then means is the cavity-based combustor could give better performance as compared to the combustor without cavity. So about objective two, I will say that the influence of dual cavity over single cavity and effect of spacing is also difficult. Then how the dual cavity could affect the performance of a scramjet combustor. And objective three, effects of fuel like hydrogen and ethylene in reacting and non-reacting flow conditions. Effect of Mach number on various fuels in a cavity based scramjet combustor. These are discussed. So objective 4 we are having comparative assessment of a various strut vector, then effect of temperature and jet to pressure ratio that we have done. And we have not done any experimentation, we have done only numerical analysis and with 2D simulation. We have not done 3D simulation, although I know that the large AD simulation, LES model, it is the best model, but due to some limitations, we have done 2D analysis. So, this is also discussed how the type of injectors could affect the fluid flow in scramjet combustor. And these are the equations, and the equations are very well known since long: continuity equation, momentum equation, energy equation. These are very basic equation of fluid flow. Then specific transportation, and here we have taken turbulent heat number. It is fixed for 0.7. Then the turbulence represents the chaotic and random state of motion of fluid elements, and its progress where the velocity and all other fluid properties change continuously along with time. And this type of flow are called as turbulent flows. And the turbulent flows are more complex and expensive due to its unsteady, and it appears in many scales. Next, the SSTK omega model was widely accepted for aerodynamic application. It includes two extra transport equations to portray the turbulent properties of the flow. And the SSTK omega turbulence model is utilized to predict the intricate physics, which includes formation of a shock wave and separation region. And the SSTK omega model is more precise than the K epsilon turbulence model and offers better prediction of jet flows and mixing rates. So we have used here SSTK omega model for our numerical analysis. So these are the turbulent kinetic energy equations for SSTK omega model. These are the formulas for combustion efficiency, mixing efficiency, and for total pressure loss. And after this, the finite rate eddy dissipation model is considered since it gives a more accurate and precise prediction as compared to the eddy dissipation model. Then boundary conditions we have chosen, and it is shown here in the figure also. This is adiabatic, no slip boundary condition is implied at the bottom and top wall. Newman boundary conditions are applied at outlet on all the variables, including pressure and temperature are extrapolated from the internal cells, and Dirichlet boundary conditions are applied at the inlet. And the flow domain is divided into a number of finite sized subdomains, and each subdomain divided into a finite grid points or cells, and integration of the governing differential equation over each subdomain. And this is the governing equation given in mathematical form. And in fact, our commercial software ANSYS Fluent, this uses finite volume method. This I can skip this slide. Then model validation, we have done grid independent test also. And comparison, we have validation study for comparison of mean wall pressure along the length of combustor for hydrogen and for ethylene also, with experiments which are done by MICA-ETL and CAI-ETL. And here for non-reacting flow, we can see here that inlet is there, then combustor, then the nozzle. So this is non-reacting laboratory scale of scale cramjet model. Then experimental, it is given in reference 2728, and we have compared with this and present work. So comparison of flow structure for density distribution, and we see that these two figures, they resemble very closely. And here also the experimental work is discussed in 18, and pressure work comparison of flow structure for density distribution, and we see the very close similarity here. Then problem statement 1, that is to investigate the effect of geometrical configuration of cavity on combustion characteristic in a strut-based scramjet combustor. So here we have seen the cavity also, L by D ratio 2 to 5, then cavity angle minus 60 degree, and result streamline distribution, combustion efficiency, pressure drop, mixing efficiency. About that we have discussed that. So these are the various parameters, and we have taken hydrogen fuel, and air is there for ignition. And here we have done grid convergence analysis, that is called grid independent study. And then length to depth ratio of a cavity, it varies from 2 to 5. Cavity angles, alpha, it is variation 15 degree to 60 degree. Offset ratio of a cavity is fixed at 1. And the results are given in the form of streamline, shock wave, combustion efficiency, mixing efficiency, and total pressure loss. So the one diagram, this is about without a cavity and this is with cavity. So the V-type shaped shock wave are observed from the tip of the strut to along the length of combustor in both configurations. And the flow disturbances are more for the case of combustor with a cavity, the disturbance is more. And here also strut-based combustor without a cavity and strut-based combustor with a cavity, it is shown. And here we can say that the recirculation region is seen in the presence of a cavity as compared to the without cavity cased combustor. And this is about mixing efficiencies. Combustor with cavity, the combustion efficiency is high in case of combustor with cavity, and mixing efficiency is also high in case of combustor without cavity, the mixing efficiency is high. So then these are the plots for L by D ratio 2, 3, 4 and 5, and these are, you can say these are self-explanatory. Then this is diagram for variation of combustion efficiency and mixing efficiency. And we see that for L by D ratio 4, the combustion efficiency it is maximum. And here we observe that for L by D 4, the mixing efficiency is maximum. Then next, this variation of total pressure loss also. So total pressure loss, it is more for L by D is equal to 4. So then effect of angle of cavity also we have discussed. That is alpha is equal to 15 degree, 30 degree, 45 degree, then 60 degree we have taken. And we see that the drastic change in the flow behavior is observed with the increase of angle of a cavity. Then variation of combustion efficiency, that we observe that the optimal engine performance is achieved by the appropriate angle of a cavity at alpha is equal to 30 degree with minimum amount of pressure loss. And here also the complete mixing takes place at lesser distance for alpha is equal to 30 degree as compared to remaining cases. So variation of total pressure loss also, it is concluded. And these are the summary of the finding. And I have already discussed this previously, so I will skip this. This is problem statement 2, what we have done, that to investigate the implication of dual cavity and combustion characteristic in start-based scramjet combustor. So here we can say again the same diagram, that strut is also there and cavity is also there and cavity 1 is there and cavity 2 is there. So this is the strut-based scramjet combustor with a dual cavity, where spacing is there, means S1, S2, S3, there are 3 spaces. And these are the parameters that we have done again, grid independent test and comparison we have done. So what we observe that the mixing gradually increases when the hydrogen mass fraction becomes smaller and smaller until hydrogen disappears. And the distribution of hydrogen is found to be more in the case of absence of a cavity as compared to the single and dual cavity based combustor. So in this figure it is observed the oxygen supply continues for longer downstream distance in case of dual cavity based combustor. And this is about variation of mixing length. So here also we are getting some conclusions. And for the case of combustor without a cavity, the mixing length increases with the increase in hydrogen mass fraction and it decreases where there is cavity. And this is the diagram which shows influence of dual cavity over the single cavity, that variation of combustion efficiency along the length of combustors. And what we observe that combustion efficiency, this is maximum for dual cavity. Then these are the diagram with variation of spacing, that is S1, S2 and F3. And we observe that the intensity of the recirculation region is found to be smaller when the spacing between the cavity is either too close or too far, that is S1 and F3, whereas it is larger at spacing S2 equal to 12.7 mm. So this is about variation of mixing efficiency. This is about variation of combustion efficiency for the 3 variation of S1, S2 and F3. And this is hydrogen mass fraction contour for various spacing and Mach number. And what we observe that mixing rate of fuel and air increases at the shortest distance of a combustor, leading to the enhancement in combustion quality. And the thermal choking problem is pronounced at higher Mach number, which leads to unsteered engine condition. Due to this reason, the reliable performance of mixing length and fuel penetration height can be obtained at F2 is equal to 12.7 mm with Mach number 2.5. That we have come to this conclusion with our numerical computation. And this is about variation of combustion efficiency. So these conclusions are there, which I have already discussed. And summary, these are the summary of the variation of spacing. And we observe that Mach number 2.5, this is optimized. Then problem 3, that to investigate the maximum characteristics of reacting and non-reacting flow condition in a cavity stratus scramjet combustor. So here also it is same thing. Here we have discussed both reacting and non-reacting flow condition. And again here, stratus is also there and one cavity is also there. And then we have analyzed Mach control distribution, static pressure, mixing efficiency, fuel mole fraction at various cross sections. So these are the estimation of errors. We have done grid independence test, and these are the diagrams of comparison of hydrogen and ethylene at the same Mach number. And what we observe that the flow disturbances caused by the cavity and the expansion of shock increases during Mach 3.5 as compared to MA equal to 2.5. Means for higher Mach number, the disturbance is more. Then size of the recirculation region depends on the thickness of the cavity shear layer and the interaction of shock waves. That we can see from the figure also. It is very, very obvious. Then this is about non-reacting flow, this is the analysis of static pressure. And here we observe that the static pressure variation along the bottom wall of the combustor for hydrogen and ethylene fuel flow similar trend qualitative due to the absence of turbulence chemistry interaction. And these we have done for Mach number 2.5, 3 and 3.5. So these are non-reacting flow mixing efficiency. And here also we observe that the complete mixing of ethylene fuel and air takes place relatively at higher distance. Then these are the diagram, and we see that for ethylene fuel, crimple type of fluid flow is observed, and the excursion of fuel increases with the increase of Mach number. That we observe, and we have compared here ethylene and hydrogen, and you can see the variation from the figures itself, and the figures are self-explanatory. And here, this is about reacting flow static pressure. So the static pressure increases significantly at the injection port due to shock-shock interaction. And for Mach number 3.5, the pressure rise is more. As Mach number increases, the pressure rise, and the peak pressure it is more. And here also molar fraction also it is seen from the diagram. And we come to the conclusion for reacting flow mixing efficiency that in case of reacting flow field, the mixing of fuel and air occurs due to interaction of turbulence chemistry and species diffusion. and mixing occurs much earlier at for Mach number 2.5, and mixing efficiency this increases. With increase in Mach number means at Mach 3.5, the mixing efficiency is very high. And this is about comparative assessment of reactive and non-reactive flow conditions. I can skip this slide. So summary of the conclusion. These are the summary of the conclusion, and already since I have discussed this, so I can skip these slides. So this is our last that problem statement 4, that is to investigate the implication of stress profile on combustion characteristics in cavity-based scramjet combustion. So this is the diagram and the stress profiles they are taken. Triangular, wedge and diamond. And inlet temperature we have taken 1050 K, 1250, 1450 K, 1650 K at distance. And we have plotted the result of shock waves, then fuel penetration height and mixing length, and in terms of combustion efficiency. And again, these are the governing parameters, and these are, we have done the grid independent test. And for triangular, these are the diagrams for various type of, three type of strut: triangular strut, wedge type strut, and diamond type of strut. And we observe that the shock wave reflections are more for a diamond-shaped strut profile, which ultimately helps to increase the fuel air mixing rate and the shear layer thickness. Then the size of recirculation zones is small for triangular and wedge-shaped strut profiles, especially at the corners of a cavity and the middle portion of a cavity. And the heated radicals are taken from the regions which act as igniter during combustion, increasing the residence time for making the flame more stable. So here, the influence of strut profile, we are seeing that diamond strut, this is having highest fuel penetration height. Then this is about influence of inlet temperatures. And we can say that temperature is found to be the highest when the diamond strut is used, which helps to increase the flame stability due to the presence of larger recirculation region. Means diamond type of strut injector, it is very efficient injector. Then next, we can see here from the diagram also that the maximum penetration height of fuel and lowest mixing length of fuel is desirable to enhance the fuel air mixing rate. And there is a sharp decline at T0 inlet 1250. And in case of triangular and wedge, the temperature is 1450 K. So this is variation of combustion efficiency along the combustor length for various type of injectors. And we observe that diamond is having maximum combustion efficiency. Then summary. This summary already I have discussed before, so I do not need to repeat the same thing. So these are the conclusions. That is effect of single cavity over without cavity. That the generation of shock wave in the cavity, it is much stronger. So combustor without a cavity means it can here the interaction of shock shear layer, we can say it is lesser, and the formation of strong recirculation region in the cavity leads to enhance the residence time to improve the mixing and the combustion efficiency in the strut-based scramjet combustor is increased. Then effect of L by D ratio and angle of a cavity. So what we can say that the enhancement of combustion efficiency and complete maximum is observed at a relatively lesser downstream distance of combustor with moderate pressure losses when L by D is equal to 4 and alpha is equal to 30 degree. When we have taken various angles and for alpha is equal to 30 degree, we have observed the peak effect. Then effect of dual cavity over single cavity. So we have shown that the dual cavity is always better than a single cavity. That is our conclusion. Then effect of spacing in the dual cavity and the Mach number. So what we have observed that for F2 is equal to 12.7 mm and Mach number of 2.5 for dual cavity, the combustion performance is means it is advisable. It is having better combustion efficiency. Then effect of reacting and non-reacting flow conditions. Our conclusion is that non-reacting flow, the minimum distribution of flow, thickness of the shear layer and the mixing of efficiency occurs at MA equal to 3.5. Although non-reacting flow has nothing to do with supersonic scramjet engine because here in engines we deal with reacting flow only, and this analysis is done just for the sake of studying that what really happens for non-reacting flow. Then here these are the conclusion of reacting and non-reacting flow conditions. An effect of strut profiles. Here we have observed that the value of combustion efficiency is found to be the highest in the case of diamond-shaped strut, whereas it is the least for wedge-shaped strut profile. Also, the maximum temperature is observed in case of the combustor diamond strut. Then effect of strut profile that optimal combustion performance we observe at T0 inlet is equal to 1650 and the combustion efficiency is maximum for T0 inlet 1450 in case of triangular and wedge shape strut. Then with this work we have got so many publications and we have got publication in journal like Acta Astronautica and there are many journal publication, at least 4 journal publication in International Journal of Hydrogen Energy out of this work. Although this is not 3D LES model combustion, it is only 2D analysis. So these are the journal publications. Then conferences papers are also there and these conferences are Scopus index conferences. Then scope of further research is also there. Like we can try large eddy simulation model and we can get better result. And these are the references and we have the many references. And out of that very less are shown here. So thank you so much for hearing patience. So I conclude this and I am happy to get the questions and I will be liking very much if the questions are asked by email so that I can answer in a better way.